In this lesson, we consider the concept of a crossed aldol condensation. So I would like to start with the definition. A crossed aldol is when the carbonyl being added to is different from the one that's deprotonated at the alpha carbon to make the enolate. So as an example, suppose you wanted to make the following compound using an aldol condensation. Okay, so this is an alpha-beta unsaturated ketone, so it is the product of an aldol condensation plus dehydration. What enolate would you need, and what ketone is the first question we want to ask. So the ketone, we're going to look at the left-hand side of the molecule, again, using the dissection of this that we had looked at in a previous lesson. We want to look at where the carbon-carbon double bond is and say the carbon furthest from the carbonyl, the beta carbon, is going to become the ketone fragment. And then the rest of the molecule, the right-hand half of the molecule, is going to come from the enolate. And of course, the enolate indicated here is generated by deprotonation of 2-butanol. Okay, so fundamentally our neutral starting materials that we would start this reaction with are acetophenone and 2-butanol, different ketones. Well, if you simply mixed the two ketones with NaOH, there would be 6 possible products, the desired product plus these 5. And to help us get through this, I'm just going to label acetophenone as ketone A and 2-butanone as ketone B, so I don't have to say the names over and over again. Okay, so we would get this product from the self-condensation of A. So A has alpha hydrogens. It can add to itself, do an aldol plus dehydration, and that would give you that product. We can get A forming an enolate, and that can add to B, which would give you product 2. Then in the case of B, we have, since it's an unsymmetrical ketone with alpha hydrogens on either side, we can have either the kinetic enolate or the thermodynamic enolate. So this third product is what you would get if the thermodynamic enolate of B adds to ketone A. Then the fourth product is what you get through a self-condensation of B using the kinetic enolate. And then finally, this fifth product would be the self-condensation of B using the thermodynamic enolate. The desired product that we wanted to get out of this reaction by the same analysis comes from the kinetic enolate of B adding to A. Okay, so with NaOH you could get 6 products, and this is not even the worst case scenario. There would be more products if A could form 2 enolates. Because A has no alpha hydrogens on one side, it can only form 1 enolate. So that cuts down the number of products. Okay, so how do we get just the product we want? Obviously, mixing the 2 ketones with NaOH is not the answer in this case. Well, the answer is that we deprotonate the ketone that will become the enolate, B in this case, completely first. Make it all go to enolate so there's no more ketone B present. So as long as the kinetic enolate is what is desired, we can use LDA as the base. Okay, remember LDA, lithium diisopropyl amide, is the base that can give us preferentially kinetic enolates. Okay, so we take our B, react it with LDA, we get the kinetic enolate, and then in order we would add it to ketone A. Then we would have to add a proton source, and then finally dehydrate it. I'll go through this in a little bit more detail. First of all, I have a word to say about LDA. Under LDA, I have written the 3 letters THF. Remember, THF is an aprotic solvent. It's the abbreviation for tetrahydrofuran. Okay, so since LDA is such a strong base, it must be used in an aprotic solvent because it will remove the proton, the acidic proton, from a protic solvent. Ether solvents are commonly used, and tetrahydrofuran is a particularly good solvent for this reaction because since it is more polar than diethyl ether, the LDA is more soluble in it. So, second of all, this reaction differs from previous aldol condensations in that we are carrying it out under non-aqueous aprotic conditions. Okay, so water is not present in this reaction, at least not at first. So in the first aldol condensation mechanism that we looked at, the OH hydrogen of the beta hydroxy ketone gets put on by the alkoxide reacting with water that is present in the reaction medium. Without water present in the reaction medium, we have to add a proton source to protonate the intermediate alkoxide anion. Okay, so the alkoxide anion is drawn here on the right of your screen. That needs to get protonated to form the beta hydroxy ketone. This is called quenching the reaction, or is sometimes called working up the reaction. And if you're doing this in a lab where you actually have to care how much to add, you need to add enough proton source to quench any leftover LDA from the first step. So since LDA is a stronger base, it will protonate first before the alkoxide will. The proton source that I have chosen to use in this reaction is ammonium chloride. It is a weak acid, but definitely acidic enough to protonate everything that we would need to make a neutral compound. So the beta hydroxy ketone can be isolated if desired in this case, or it can be deprotonated with heat in order to induce dehydration. Now you may wonder, we are adding to a ketone here, and we've talked about the fact that aldol reactions in which you add to a ketone are not going to be, in many cases, will not be thermodynamically favorable and would want to go back to the starting materials. Well, that statement was true under the conditions where you only have a small amount of enolate present. So remember, when you use NaOH as the base to deprotonate, you only have a small amount of enolate present because that first acid-base reaction is unfavorable. However, in this case, where we use LDA as a base, we have a large concentration of enolate present. We have a 1-to-1 stoichiometric ratio of enolate to the added ketone. And in fact, we frequently add the ketone dropwise so that there is an excess of the enolate present. So by these concentration effects, this equilibrium gets driven to the right to the conjugate base of the beta hydroxycarbonyl. Okay, so in this case, you can actually stop at the beta hydroxy ketone, and it's not going to go backwards on you, or at least it may to some small extent, but not to an appreciable extent. Or to get to the product that I've indicated, you can dehydrate. The last question that I would like to consider in the context of this lesson is, can we do a practical, meaning high yielding, not giving 6 products, crossed aldol condensation using NaOH as a base, or is LDA the only option? The answer to that is that crossed aldols that yield a single product can be carried out with NaOH as the base under a couple of very specific conditions. Namely, that an aldehyde with no alpha hydrogens needs to be combined with a ketone with only one type of alpha hydrogen. Okay, so we're going to look at 2 examples. In the first example here, we have an aldehyde with a tert-butyl group on one side, which means that it has no alpha hydrogens. Obviously, on the aldehyde side, there's no alpha hydrogens because there's no alpha carbon. We're going to react that together with acetone. Acetone will get deprotonated by NaOH to form the enolate, and then you can get the beta hydroxy ketone product from the enolate of acetone adding to the aldehyde. And you should note that we don't have to worry about self-condensation here. The ketone enolate will not add to itself because, as you remember, aldehydes are more reactive than ketones as electrophiles, so that enolate's going to want to add to the aldehyde. As a second example, if you take 2 molecules of benzaldehyde and react it with acetone and add NaOH, you actually get this interesting molecule here that's called dibenzylidine acetone. So in this case, the enolate can form on each side of acetone. Again, if you look at the product of the first reaction in example 1, that still has a CH3 on the other side of the carbonyl. There is nothing to stop that from getting deprotonated by NaOH and adding to another molecule of aldehyde other than the aldehyde being all gone. So if you use 2 equivalents of aldehyde plus acetone, you get a double aldol. An aldol happens on each side. And in this case, dehydration takes place spontaneously, even at room temperature, because of the extended conjugation that is generated in this molecule. Okay, so that's your lesson on the crossed aldol condensation. We've got one more lesson on aldols where we will consider the intramolecular aldol condensation.